Hey guys, welcome back to the channel. Now, this is the 8th video in the STM32 programming series, and in this video, we will be taking a look into interrupts. But before we get started, I need to tell you that interrupts is a rather broad and involved topic, as each and every microcontroller peripheral has its own interrupts, and there are lots of them, so there is lots to cover. But in this video, to keep things limited, specific, and focused, we will be only discussing GPIO interrupts. So let's get started. So what are interrupts? Well, interrupts are these events that can happen at any given point in time, or on the other hand, they can also happen periodically. And that totally depends on what type of interrupts you are dealing with or the microcontroller has been configured to deal with. So let us take a look into a real life interrupt scenario. So say for example, a real life interrupt scenario may look like this. You are working on your computer, doing some next level shit, and then you get a call, a rather important one that needs to be answered. So you answer it, and then you get back to work. So the part where you are working on your computer is just a CPU processing the code in the while one of your main function. The phone call is the interrupt. You accepting the phone call and talking on the phone is basically the CPU or the microcontroller serving the interrupt in an interrupt service routine, or ISR for short. That is basically just a function written in C. And then you getting back to work is the CPU getting back to what it was executing before. Okay, let's say for example, a user pressing the user button on your STM32 Nucleo board. Now this is an event that can happen at any given point in time, and after the user presses the button, there are some actions that need to be taken on your STM32 Nucleo board. Say for example, turning on an LED, just to begin with. So how do we tackle this problem? Well, in the 6th video, what we did was we repeatedly checked the status of your button. Like, is it pressed? Is it pressed? Is it pressed? We kept on checking that inside the while one. But there's an alternate and a better way to do that, which is of course with interrupts. So now the idea would be to start the STM32 Cube IDE and program the Nucleo board and configure the user button as an interrupt. But before we go ahead and do that, here we have the reference manual, and we are in section 14.2.6. And here you can see the EXTI lines and basically how the GPIOs have been mapped to the EXTI lines. So these are pins from port A, pin 0 to all the ports, but pin 0 of all the ports, and then pin 1 of all the ports, and so on. And then we go up to pin 15 of all the ports. So and you have to write C functions which can basically handle these EXTI interrupts labeled for these specific numbers. Now the user button on your Nucleo board is port C, pin 13. That means we will have to write a function for EXTI 13. And if I scroll further down, there are more EXTI lines assigned and dedicated for some other peripherals like RTC, USB, and then some comparators. And then we also have I2C, USART, some more comparators, and then some more UARTs. And then there are some EXTI lines that are internal. So let's get started with the coding part. Alright, so here we go. We have the STM32 Cube IDE open in front of us. Now I have applied a dev style dark theme just to reduce the strain on my eyes while I'm coding. Well, nothing fancy. So I'm going to go in File, New, and then create a new STM32 project like we did in all the previous videos. So I'm going to go in board selector and then type in F303RE because that is the board I'm working with. Select this one and do next. Let us add a project name and then type in button underscore interrupt. That will be the name of our project, and then just do next and then copy only the necessary library files. Then click on finish. yes, initialize all the peripherals with their default mode. So here we have our device configurator tool open in front of us. I'm going to go in system core, and then I'm going to go in GPIO, and in the default or the basic configuration of the Nucleo board, PA5 has been already configured as LD2, which is the onboard LED, and then PC13, which is port C pin 13, has been already configured for us as the B1 button. And now if I click on it, then it has been already configured for us as an external interrupt mode with falling edge trigger detection. So whenever the particular GPIO drops from the 3.3 volt line, because if you remember what we discussed in the user button GPIO input video, the GPIO is actually externally pulled up through a resistor, and when you press the button, the GPIO input line falls low to ground. That means we need a falling edge trigger detection. And if I click on it, then there's a rising edge trigger detection, and there's also a rising or falling edge trigger detection when you don't actually know when exactly do you want an interrupt, or the interrupt can be both rising and falling. But for this particular example, we'll be going ahead with external interrupt mode with falling edge trigger detection. There are also external events, but those are subject to some other video. But yeah, let's select falling edge trigger detection. Next up, we want to go in the NVIC. Now the NVIC stands for Nested Vectored Interrupt Controller, and these are all the interrupts that are available right now. And then what we have to do is we have to select this particular EXTI line, which stands for extended interrupt. And I'm going to select this particular checkbox over here. And for code generation, make sure the IRQ handler, the interrupt handler, has been ticked for the EXTI line 15 to 10. So basically the PC13 GPIO responds to all these this particular EXTI line, and then you get a particular IRQ handler. So there can be several other GPIO pins which when get an interrupt go to this particular IRQ handler, and then make sure to also call the HAL handler. So let's actually generate the code and see what do these check boxes actually mean. So I'm going to click on the generate code button. Okay, so here we go. We are in the core, and then we have the main.c open over here. Yes, but what we do not see in the source files is there is no GPIO.c, because we forgot to do that. So let's go back in project manager, I believe, and then code generator, and then generate peripheral initialization as a pair of .c and .h files. So everything that is related to GPIO goes in a nice and dedicated GPIO.c file. So things have changed now, and then I'm just going to hit on generate code again. All right, so here we go. We have the GPIO .c over here, which has the MX GPIO init function. Now what matters now is everything is actually initialized for us, like we saw in the previous videos, the button and the LED. Now my target over here is to write a program that if you press the button once, you get an interrupt and I turn on the LED, obviously in the interrupt service routine. And if I press the button again, I turn off the LED again in the interrupt service routine. So basically there would not be any code inside this while one function over here. anything and everything you do will be based on interrupts and the interrupt service routine. So let's see how to do that. For that, we need to open this particular file over here, which is the STM32 F3 XX underscore IT, and that has all the interrupt service routines. Now I'm going to pause over here and just enlarge the font size. Okay, here we go. And now, as you can see, these are all the interrupts which are already configured for you, because these are some serious interrupts like a hard fault interrupt and an NMI handler, which is a non-maskable interrupt. Again, all these things are out of scope of this video, and like I mentioned, interrupts is really an involved and a broad topic, and we are only talking about GPIO interrupts in this video to begin with, especially. So what I'm going to do right now is go to the EXTI 15 underscore 10 underscore IRQ handler function, and then this thing is actually calling the HAL GPIO EXTI IRQ handler for the GPIO pin 13. So now if we go back to our device configurator tool, so this particular checkbox over here, which says generate IRQ handler, actually generates this function over here. And the second checkbox, which is the call HAL handler, actually generates this function over here. So whenever I press the user button, which can be any given random point in time, my code will actually come inside this particular IRQ handler. So how do I know that? Because, well, we don't have any UART set up at the moment, and neither do you have any printfs, and we don't even know if the LED blinking will work. Now the easiest and the fastest and the quickest way to do that is to just double click over here and set up a breakpoint. So I'm just going to set up a particular breakpoint. So whenever I press my user button, the code will come over here and halt at this particular breakpoint, and that can be any given random point in time, because the processor can be doing tens and hundreds of things inside the while one, or in this scenario, basically nothing. So what I'm going to do next is compile. There we go, 0 errors and 0 warnings. And as usual, we need to create a debug configuration because we have just created a new project. And since we have already compiled and there are 0 errors and 0 warnings, we already have the ELF file. If not, you can click on search project and actually search for the ELF file inside the debug folder. Next, I'm going to go in the debugger. We will be using the serial wire debug interface, and then I'm going to scan for my particular ST link, which is already connected to my Nucleo board. I'm going to click on apply, and let's go ahead and debug this. So here we go, the code has been successfully downloaded and verified, and it has halted for the first line inside the void int main, which is HAL init. So I'm going to press on play or resume, and then, well, basically nothing happens because the system initializes the clocks, and then your processor is just basically doing nothing at all inside this while until I go ahead, unless I go ahead and press the user button, which is this blue button on your Nucleo board. So if I press that, let's see if we get an interrupt. Here we go, I've pressed the button and the code has come inside. The execution has halted at this particular IRQ handler for our GPIO. And then I press the play button again, and then now we are back again inside this while one. Let's do that again, and here we go, we got another interrupt. So I'm going to stop the execution now. All right, so now let's make the LED work with the button interrupt. I'm going to remove the breakpoint we have over here, and let us take a deep dive into the HAL GPIO EXTI IRQ handler function. So I'm going to press F3, and here we go. Here we have the function. So that can be found in the STM32 F3 HAL GPIO.c file. So whenever an EXTI line interrupt is detected, I actually go and check whether that line has been asserted. That means, is this particular interrupt line for this particular GPIO pin, which is the GPIO pin 13 in our scenario. And well, how do I check that? I can just go in main.h, and then I have the B1 button pin as GPIO pin 13. Coming back, so did we actually get an interrupt for this particular pin? And that is not equals 0, which means if I got an interrupt, that means that I have a 1 over here, and 1 not equals 0 is true. So then I successfully go inside the if statement, and then I make sure to specifically clear that interrupt assertion. By doing that, every time unnecessarily I don't make this particular if statement go true, and then we keep on going inside this if statement again and again. So next up is the HAL GPIO EXTI callback. So this is a callback function which is defined right below the EXTI IRQ handler function. Now, what is special about this function is that it has the keyword weak associated with it. That means it is, well, weakly defined. And there's a note over here which says this function should not be modified when the callback is needed. The HAL GPIO EXTI callback could be implemented in the user file. Now, this can be any user file, but we need to declare this function with the same name without the weak keyword. That means we need to define it well, strongly, and well, not with the weak keyword in a weakly manner or in a weak sense. What will happen then is the compiler actually sees two function definitions of the same name, but one is without the weak keyword. And when that happens, the function with the strong definition, or well, without the weak definition, is actually executed. So let's go ahead and write this function in our HAL GPIO.c file, and like I said, without the weak keyword. Now in this function, we actually would write the code to make the LED glow whenever we have pressed the user button. So I'm going to declare a variable, let's say bool previous val, and then I go if the GPIO pin is actually the same one as my B1 pin, because well, there can be a lot of pins for that particular GPIO interrupt. So I need to be sure that I'm writing it for the GPIO pin 13, because this particular IRQ handler can pass a lot of other GPIO interrupts as well. So whatever I do, let's make sure we are only doing it for this particular GPIO pin. And let's also take our variable inside this if. So here we go, we have bool previous val. Also, let's make it static so it maintains its previous value. So what's happening here is whenever this function is called for the first time, a variable named as previous val is declared, and it's a boolean, so it can only have two values, true or false. More importantly, it's a static. So let's say it's false, it's 0. So yes, it will go inside this if statement and the LED goes high, and then I set it to true, and then the else part is not executed. The next time when we get an interrupt or we press the user push button, the variable is declared again, but since it's a static, it will maintain its previous value, which was true, and then it will not go inside this if statement. It will go inside the else and then reset my LED. Then we declare it as false. So it would be an alternate execution between if else every time we keep on pressing the button. Let's go ahead and check for errors. Oops, so we have 4 errors, and that is a result of false and true is undeclared. So we need to go up and include the stdbool.h file. And now let's try again. There we go. Nothing, not a good, any good site, like 0 errors and 0 warnings. Let us go ahead and flash this. Here we go, our code has been flashed, and now again it is executing basically nothing inside your while one. Now let's go ahead and press the user button, and here we go, our LED is on. Press it again, LED is off. Then we can keep on doing that, and nothing is inside the while one. Everything is based on interrupts. So yeah, that is about it for this coding session. Alright, so that's how you configured a GPIO interrupt. Now there are lots of other peripherals that also have interrupts, like say for example the UART or SPI. I'll give you a quick example when it comes to UART. Let's say your nuclear board or STM is connected to some UART module, and the UART module can send the data to your STM32, obviously over UART, but again at any given point in time, at any random instance. So then you can also configure the UART to receive with interrupts. So whenever you get some data over the RX line, you get an interrupt, you process that data, store it in some buffer, and then you probably print it on the screen. So things like that. But there are also some tricky questions that you can try answering. Like say for example, the CPU or the processor is actually serving an interrupt. So let's say there are 5 or 10 lines of code inside the ISR. So one interrupt has already occurred and the CPU is busy serving that interrupt. What happens if you get another interrupt from any other peripheral? What happens then? So that's basically an interrupt inside an interrupt. How do you tackle that? If you know the answer, make sure to let me know in the comments below. If not, I can discuss that in some other video. So well, that is about it for this video on interrupts. Make sure to leave a big thumbs up if you like this video and if you found it helpful. And as always, see you in the next one.